CERN isn't known for space missions, but a wave of online claims said its scientists just attempted to intercept the strange interstellar visitor. Rumors of secret probes, exotic sensors, and classified launches exploded across the internet. But what really happened? Here's what the science says and what it doesn't. Subscribe for updates. Discovery of 3I Atlas. On July 1, 2025, the Atlas Sky Survey in Chile detected a fast-moving object cutting across the sky, later designated 3I Atlas. It was moving too quickly to be a typical asteroid and followed a path that didn't close into a loop. Orbital calculations confirmed it was on a hyperbolic trajectory, meaning it was not gravitationally bound to the Sun. It was coming from interstellar space. Within days, astronomers began combing through older data, and pre-covery images from TESS, CSS, and ZTF revealed the object had been faintly visible weeks earlier, already showing signs of activity. This meant it was likely shedding material, while still far from the Sun, an unusual trait for any comet. As 3I Atlas moved inward, its appearance became more comet-like. A diffuse coma formed around the core, and a growing tail extended behind it. Unlike typical comets, though, its light showed signs of reddening, especially at larger distances, which deepened as it approached perihelion. Spectroscopy added to the mystery. Early results showed the coma was not dominated by water vapor, but by carbon dioxide, a volatile seen in some comets, but not usually in such abundance. This indicated a CO2-dominated chemistry, possibly tied to how and where the object formed. Water, carbon monoxide, and other typical gases were present, but in much lower quantities than expected. Polarimetric observations added another twist. The object displayed negative polarization at small phase angles, a signature distinct from solar system comets. This suggested that the dust or particles in the coma had a unique composition or structure, possibly originating from a different kind of planetary system altogether. From the start, 3I Atlas was not behaving like any comet astronomers had previously catalogued. It was comet-like in activity, but not in chemistry, trajectory, or physical structure, and its early behavior raised questions that no existing comet model could fully answer. Anomalies and speculations around 3I Atlas. As more data came in, the unusual nature of 3I Atlas sparked debate across the scientific community. Harvard astrophysicist Avi Loeb was among the first to publicly suggest it might not be a typical comet. He pointed to its trajectory, light behavior, and unusual chemistry as grounds for considering non-natural origins. Loeb emphasized that the object's path, emerging from the southern celestial hemisphere and inclined just slightly off the solar system's plane, was unlike most known interstellar entries. Its speed and angle resembled the kind of path a targeted flyby might follow, though no propulsion or maneuvering had been observed. At the same time, the object's chemical ratios, particularly the high CO2 levels, drew attention. Other comets do contain CO2, but few, if any, show it in such dominance. The presence of water vapor and carbon monoxide was weaker than usual. This pointed to an origin in an extremely cold, possibly carbon-rich region of space, or an environment different from those that formed most known comets. NASA and most planetary scientists responded cautiously. They acknowledged the object's anomalies, but emphasized that it was still behaving like a comet in key respects, forming a coma, shedding dust and emitting expected volatile signatures, even if in odd proportions. No artificial features had been confirmed. One striking observation was the detection of OI emission, a proxy for water vapor, when the object was still 3.5 astronomical units from the Sun. This level of early activity required a large active surface area, possibly due to embedded ice grains or volatile-rich regions exposed on its surface. While many researchers dismissed alien theories, few denied the object's strangeness. The working theory became that it was a very old, possibly chemically altered comet ejected from another star system long ago. Still, for some, the combination of orbital precision, chemical oddities, and deep space behavior left open the door to more controversial interpretations. The idea of intercept missions. What would it take? Intercepting an object like 3I Atlas is more than ambitious. It is near the edge of what current space technology can achieve. Because the object is moving on a hyperbolic trajectory, Any spacecraft hoping to catch up must reach extreme speeds well beyond Earth escape velocity. The required delta V, or change in velocity, makes a direct intercept incredibly difficult, unless launched shortly after discovery. Timing is critical. As 3I Atlas accelerates toward the Sun, the energy needed to reach it grows rapidly. A viable intercept window would have required mission planning and launch months, possibly years, before the actual discovery. Once it passes perihelion and starts heading back out, the chance to catch it diminishes to almost zero with current propulsion systems. Even if speed were not an issue, the payload would need to be small and highly specialized. A probe might carry instruments for spectroscopy, dust sampling, and particle detection, perhaps microp robes or beacons designed to fly through the coma. The challenge is not just launch and speed, it's surviving solar radiation, achieving accurate targeting, and maintaining communication over massive distances at high velocity. Theoretical designs have been proposed. Concepts like laser sails, electromagnetic propulsion, or even high-velocity kinetic flyers have been discussed in academic circles, but these remain untested at the necessary scale or speed. Gravity assists from Earth, Venus, or Jupiter could help save fuel, but they introduce long delays, time that 3I Atlas doesn't give us. Despite interest from researchers and institutions, there's no confirmed intercept mission in development. Discussions are ongoing about using existing spacecraft, like repurposing a flyby window from a mission such as Juno or the Parker Solar Probe, but trajectories don't align closely enough for a true intercept. As it stands, the best data we can gather will likely come from remote observation. Even with the desire and scientific payoff, the technical hurdles are enormous. Any real attempt to intercept would need a fundamental breakthrough in propulsion planning or international coordination, none of which happened in time for 3I Atlas CERN's hypothetical role in a mission to 3I Atlas. Though CERN isn't a space agency, its expertise in particle physics and materials science could be valuable in any future mission to interstellar objects like 3I Atlas. If a probe were ever launched, CERN could help design ultra-sensitive detectors to analyze rare particles or isotopes in the object's coma, especially if its composition suggests an unusual or non-natural origin. Detector technology used in CERN's collider experiments could be repurposed for identifying exotic particles or radiation patterns. Its work in vacuum environments, high-energy shielding, and radiation-resistant materials might also contribute to designing spacecraft that could survive the harsh conditions near. 3I Atlas.CERN's massive computational power could be used to simulate interactions between the comet's emissions and the solar wind, especially useful if the object behaves outside typical comet models. This could guide mission planners on what data to prioritize during a flyby or sample collection. While CERN can't launch missions, it could collaborate with NASA, ESA, or commercial partners by supplying instruments or analyzing returned samples. If 3I Atlas ever yielded physical material, CERN could play a key role in analyzing isotopic ratios, rare elements or unknown compounds. However, there's no confirmed probe, no secret launch, and no official CERN involvement in any intercept. All claims of a mission remain speculative fiction. What's real is the growing interest in cross-disciplinary partnerships for future interstellar missions. The real value of CERN's potential role is this. As our technology evolves, we'll need the combined expertise of space science and fundamental physics to decode what these mysterious visitors bring. 3I Atlas may not have been intercepted, but its presence may have started a new era of scientific cooperation, bridging Earth's most advanced labs with the frontiers of space. What if CERN intercepted? Possible scenarios and outcomes. Let's imagine a speculative scenario. CERN, using its expertise in detectors and materials science, partners with a space agency to launch a microprobe aimed at intercepting 3I Atlas. The goal isn't to land, but to fly through its coma, collect particles, and return data on gas emissions, magnetic fields, and radiation anomalies. If successful, the mission could deliver profound results. In Scenario A, the probe collects cometary particles containing unique organic compounds or previously unknown isotopes. Analysis might reveal molecules never observed in our solar system, offering clues about planetary formation or even prebiotic chemistry from another star. Scenario B features a close flyby with high-resolution imaging. The probe sends back structural data, revealing whether the object is monolithic, fractured, or composed of layered materials. Spectroscopy might uncover mineral patterns or trace elements inconsistent with known cometary bodies. In Scenario C, something unexpected occurs: sharp magnetic spikes, shifts in emission spectra, or even data dropouts. Instruments register anomalies that don't match known natural processes. The data sparks global debate. Was it equipment failure? Or did the probe detect something truly unexplained? But even in fiction, risks abound.